als jij je voor iemand die superdator.
Okay, good afternoon. So let us start the last part of the lesson. I will skip a little bit of proofs today so that we go back to the integral ones that we skipped. Might be that's a little bit more important. So sequences and series of functions. Okay, so this is the first thing we want to talk about today. Okay, before starting the first slide, let me just introduce you the concept. So far, we have sequences. Forget about series for the time being. Let us start with the notion of sequences of functions. Okay, so far we have learned about sequences of numbers, or in general sequences in metric spaces. But here, forget about metric spaces. We are working only in the set of real numbers. So the sequences we had are in real numbers. So if you have a sequence A sub n, this is a sequence of numbers. It means that you can list them, and each one of these terms is a real number. Okay, a sequence in R. But now, as the name suggests, this time we have a sequence, but each one of the elements is a function. Okay, so we have a sequence of functions. But you know that functions has rules and domains. We consider that the domain on all of them are the same. So this means that, for example, I would say let D be a subset of R. Okay, and for every n in n, f sub n is a function defined on this domain D, and let us take the codomain R. Okay, so when you have a sequence of functions, in general you can have sequences of functions with different domains, but that is not very helpful. So we always assume that the domain of all the functions are the same. So, for example, let us take it D, the subset of R. Okay, the first question we had for sequences was that, is my sequence convergent or not? Okay, but if it converges to a real number. Okay, but here, when I'm talking about a function in principle has infinitely many information encoded in it, because it gives you one value for each value of the domain. Okay, so we want to give meaning. What is the meaning of a sequence of functions approach to another function, converge to another function? Okay, so that's the first thing. So for example, let us say that I have also another function. I have another function with the same domain D and R. We want to make this more rigorous. What do we mean when we write F approaches F? We want to give a meaning to this. Okay? So we have a sequence of functions with domain D. We have another function with the same domain D. We want to give meaning to this idea that a sequence of functions converges to F. One of them, that is what you see here, it turns out that we have two notions of convergence here. One notion of convergence is too weak to keep the expectations, to our expectations. Another one is quite good. Okay. But if you don't read the slide or whatever, there is one thing that you can always think about. Yes, you can say that, okay, I can pick one particular element from my domain, and instead of looking at functions, I will calculate my functions at that point. Then this is not a sequence of functions anymore, because x is a number in my domain. When fn acts on x, it gives me a real number. So even though this sequence is a sequence of functions, but this sequence is a sequence of numbers. And f of x is also a number. Then we know what is the meaning of a number approaches to a number. based on what we learned in the sequences of real numbers. So this is one way of defining convergence, and that is called pointwise convergence. The reason is that we want to check the convergence point by point. So, for example, if I choose x in D and I set up this sequence and I set up this value, I see this is true. There is no guarantee if I change x to another number, x prime, and I do the same process, because f of x prime, f sub n x prime, in principle is a totally new sequence. There is no guarantee that if the previous sequence converges to this, the new sequence also converges to f of x prime. Okay, is the idea more or less clear? So this is the first thing we want to define then. Okay, so that is easy, and handling this is also very easy. So I would start with definition 14.1. Okay, so again, exactly what I wrote here above. So so D is a subset of R, and for all n in N, I have the function f sub n is a function with domain D and codomain R. And we also have another function, a fixed function with the same domain D and codomain R. We say that Fn converges to F pointwise, I put a P on the arrow, on D. This is what we want to define. This if and only if what happens for all x in the domain D, the sequence f sub n x, which is a sequence of real numbers, converges to f of x. Okay, so if this happens, we say that this sequence of functions converges to this function pointwise on T. So if I want to translate it in the epsilon, I haven't written it down, might be this is good you add it, because how can I define it in terms of epsilon and things like that? We have learned in analysis. We can say that Fn converges to F pointwise on D if and only if what happens? If and only if for every x in D, this happens. But this happens in the language of epsilon is for every epsilon, there exists a natural number such that if n is greater than or equal to n, this implies that the distance between them, because we are working in R, so this is epsilon definition of pointwise convergence. Is that right? Extremely simple concept, okay? So I think I have explained this for you. So let me read it again. So in this definition, the point x in D is fixed. This is good to know. Is fixed before the limit is taken. Thus, pointwise convergence means that for each fixed x, the numerical sequence f sub n of x converges to the real number f of x. The value of the limit may depend on the point x, of course, because if you change, you have completely different new sequence, yes? Okay, so that's good to read. Okay, this one, an extremely simple concept. So we want to see that if this is the case, find the pointwise limit. So a function is a sequence of functions are given to you, f sub n from R to R, defined in a very simple way. F sub nx is that x divided by n. Find the pointwise limit of this sequence on R. Okay? So that is what we want to do. Okay, so let us try to do it in a simple way. So how do you think about the problem? So a sequence f sub n from R to R is given defined in this way. F sub n of x is x to power n. And we want to answer this question, is there any function so that fn converges to that function pointwise on R? You want to answer that question, okay? So what do? You just say that, okay, let us fix x. So we say that let x be a fixed element from my domain, okay? So at this level, x is a variable. But when I say let x belongs to R, it means I fixed x. So x is no longer a variable. Then what happens if I want to write fn x? So then the sequence, the numerical sequence fn x becomes what? Becomes x over n. But again, don't think you have two variables. You have only one variable here. X is fixed, n changes. Okay? So do you think that this sequence converges? So let us write some of the terms. What is the first term of this numerical sequence? This sequence is a sequence of functions. This sequence, even though still you see x there, but because x is fixed, it's a sequence of numbers. So if I ask you what is the first term of this numerical sequence, what's that?
X.
X. But x is number, fixed there. What is the second term? X over 2. What's the third one? X over 3, and it continues. The nth one, and it continues. Okay, so what is the limit of this sequence? X is fixed, 5, 7, 10, and whatever. And then you are sending n to infinity. So it goes to 0. Is that clear? So this means that the limit of x over n goes to infinity for a fixed x is 0. Okay? So this means that this sequence of functions are converging pointwise. For every point, you converge to 0. But you cannot say that 0 is the limit, because the limit should also be a function. But that is a function whose value is always 0 regardless of what you choose for x. What is the name of that function? A function that gives you 0 all the time.
Constant function?
Constant, the 0 function, or the constant function. But you have to write it precisely. Yeah. So, okay. Therefore, this fn converges to the 0 function. This is important to write. If you leave it like that, it's not complete. So to the 0 function on, which is the domain on, the domain is R. And this problem finishes here. Okay, so is that clear?
So you could also say f of x equals 0.
Yes, you can say that, therefore it converges to this function. But you have to write the domain as well.
Yeah, of course. Yeah.
That's also good. The point is that, understand that the limit is not a number, the limit is a function. Is that clear? Okay. So, what about this one? This is a little bit more interesting. Very simple, by the way. So let us, you can read it and write the problem. We have a sequence of functions, f sub n, but this time they are defined on the closed interval. How? F sub n x is x to power n. Find the pointwise limit of this sequence here. This is what we want to do. Okay, again, you will start with the same idea. So you would say let, okay, so in principle, you will start with this sentence, but sometimes you see that because of practical purposes, you have to divide your values to different values, okay, as you see here. For example, if I just say that let x belongs to 0 and 1, okay, any number between 0 and 1, including 0 and including 1, then you see that the limits are different. Do you agree? For example, if I choose x to be 0, what will be my sequence of numbers generated by putting 0? all of them will give me 0. So I will get a constant sequence of zeros, which definitely converges to 0. If I put 1/2, for example, what happens? It becomes 1/2 to power 1. The next one will be 1/2 to power 2. The next one will be 1/2 to power 3. But if I continue indefinitely, this sequence of numbers will converge to 0. So for 0, it was 0. For 1/2, it is 0. So do you agree for any number here, it will be 0 except one special case, and that is 1. Because if I just choose 1, then 1 to power n is 1. So I will get a sequence of 1s all the time, which will converge to 1. But you have to just write this in a formal way. So you understand that this is not a good idea. So I would say that let x belongs to 0. Okay, we can consider two cases. Case 1, if x is between 0 and 1. Case 2, by this analysis, we understand that we have to do it in two ways. So if x is between 0 and 1, then what happens? Then I will have f sub n of x is x to power n. You see, don't fall into this trap. I am repeating the same thing, but this is different from there. Here x is a variable, here x is fixed between 0 and 1. Okay, so then I will take the limit of f sub n x when x goes, when n goes to infinity, because x is fixed now. And this is something you already studied in the calculus. Yeah? So what's the limit? Is 0 because x is 0. Okay, but now, so this is number 1. Number 2, if x is equal to 1, then fn x becomes fn1, becomes 1 to power n, becomes 1. So therefore, the limit of f sub n x, n goes to infinity, becomes the limit of 1, n goes to infinity, which is 1. But this is not enough. Finally, in the test, you have to write the function who is the limit. So we learned everything, but so what is the limit finally? So I would say that f of x, f is defined on R to R. So no, sorry, it should be on the same domain. 0, 1 to R, but what is that? F of x has two different values. Yes, it becomes 0 if x is between 0 up to 1, 1 not included, and 1 if x is equal to 1. So this is what we expect in the test to write as the final answer to the problem. So very simple idea. Okay, so now we want to make trouble for ourselves. So because this is always mathematics, you just make trouble. The reason that we want to make trouble is very clear in this example, because we want to preserve the analysis, so the analytical properties of your functions. For example, here I am facing with continuous functions all the time. So each one of these functions individually are continuous because these are x to power n. But then what happens? The final result is not continuous. So the limit function is not continuous because it jumps at one point. So the pointwise convergence is not that strong to keep the properties that we like intact. Okay? And that was the motivation behind a new definition. This new definition will keep continuity, boundedness, I don't know, I think uniform continuity, I'm not sure about uniform continuity, but integrability intact, but it is not strong to keep derivative intact. And the derivative part is not part of your course. I have written it in the notes, but it is optional, so you don't need to study it for the first few. Okay, so now we want to define uniform convergence now. So let me read it for you. So let D be a set, and I have again my sequence of functions. We say that this sequence converges uniformly on D to another function if for every epsilon greater than 0, there exists a natural number capital N such that the difference between fnx and fx is less than epsilon for every n greater than or equal to n and every x belonging to D. And this is the notation we use. Instead of putting a letter P up there, we put a letter U up there, which means this is uniformly continuous. But can you see the difference now? So let us explain this now here. So 14.5. So again, I have the same setup. So let me copy and paste. So D is a subset of R for every n in the natural numbers. I have a function with domain D, codomain R, and I have a function, fixed function with domain D, codomain R. Okay, so we want to define this, but for letter U, uniform. So we say that Fn converges to F uniformly on D if what happens? So if and only if this will move here. Okay, so it means that for every epsilon, you can find a fixed natural number so that for every x in D, this works. Yes? So here, for every x and for every epsilon, you need to find an n. In this n, technically speaking, depends on x and epsilon. But if this n does not depend on x, only depends on epsilon, then you have the notion of uniform convergence. Is that clear? So the only difference is that instead of putting this first, I put it here. That notion of pointwise convergence changes into the new notion of uniform convergence, and you see that, of course, this is a stronger. You remember, we were not able to interchange. I told you at some point that existential quantifier and universal quantifier are not commutable, but one of them implies the other one. This one implies that one. Okay, so what does it mean? There is a theorem that I have mentioned. So if this is correct, of course this will be also correct. Yes? Any questions? Yes?
So in this case, 14.3 has uniform convergence and 14.4 don't have it.
Yes. Yeah. Okay, so let me read this one for you, might be that's good. So the main difference between pointwise convergence and uniform convergence is the role of n. For pointwise convergence, after x in D has been fixed, the index n is allowed to depend on both epsilon and x. Thus, different points of the domain may require different indices before the values of f sub n x become close to f of x. For uniform convergence, the index n may depend on epsilon, but it must not depend on x. The same n must work for all x in D. Okay? So this is why uniform convergence is strong. It controls the error on the whole domain at once. Okay, any questions? Okay, so we can skip this theorem because we already told me. So remember that. Because if I have this, yes, so the theorem tells me that uniform convergence implies pointwise convergence. Yes? It's a good theorem to know. Do you agree that if this occurs, I can go from here and conclude that one? Yes? But not the other way around. Okay, so it's important to know. Uniform convergence implies the pointwise convergence, but as you see in this example, we will talk about this later, not the other way around. Okay. But this theorem is useful if we want to investigate whether a sequence of functions converges uniformly. We usually first study pointwise convergence. this gives us the only possible candidate for the uniform limit. Because you know why? Usually they ask you to prove, they give you a sequence of functions and they ask your opinion. Do you think that this sequence of functions converges pointwise on D, on the domain? Usually when you want to prove the limiting process, having access to the limit is important, because if I give you the limit, then you can put it in the definition and try to adjust epsilon and delta in a way that it works for you. So this is very good. But pointwise convergence is easy. Hopefully you realize. So what you do, if I ask you in the exam to ask your opinion about if this convergence of this sequence of functions is uniform or not, it is good to have access to the limit function if it exists. So it means that in a scratch paper or something, or even in the paper, you go and do the pointwise and get a candidate. If it is going to be uniformly convergent, it should converge to the one with the pointwise property. Okay? So this is important to know. That's the meaning of this remark. If we want to investigate whether a sequence of functions converges uniformly, we usually first study pointwise convergence. This gives us the only possible candidate for the uniform limit. Indeed, if f sub n converges uniformly to some function f, then it must also converge pointwise to the same function f. Therefore, after finding the pointwise limit, there are only two possibilities. The sequence converges uniformly to this pointwise limit, or the sequence does not converge uniformly at all. So thus, pointwise convergence is often the first step, even when we want to study uniform convergence. Okay? So let us go back to this example. But before doing that, let me give you a geometrical picture, which is useful to know, okay, before going to this problem. So if you want to understand if a sequence of functions converges to a given function uniformly, it means like this. So if I have this, let us say that this is my domain somewhere. So let us say that this is domain D, and I am defining my functions here. And let us say that I have this function. So I have this function. For example, this is the function f, the limit function. Okay, so this is the function f. Okay, and let us fix one epsilon. So this means that if I shift this epsilon upward, I cannot draw, but imagine that I am shifting it with epsilon upward, okay? And then if I shift it epsilon downward, something like this. Okay, so this is epsilon downward. So you shift your function epsilon upward and epsilon downward, and then you have also a lot of functions, a sequence of functions. They also have a graph on this domain. If the graph of all of them lies in this band, from some index onward, might be some of them stick out from this band in the beginning. But if one of them is completely inside this band, and everyone after that index remain in this band for every epsilon, not just this epsilon, for every epsilon, no matter how small the epsilon is, then it means that the sequence of your functions are converging uniformly to this function f. Is that clear? So that's the idea. So for example, after some, if this is the graph of your function, it remains, for example, if this is fn, and for every n greater than or equal to this fixed n, the graph of all these functions lie in this band. If that is the case for every epsilon, no matter how you make it small, of course, when you make it small, as epsilon is smaller, might be some more functions will stick out, but still, from some point onward, all of them remain in this band. If that is going to be the case, then you have the function. So uniform continuity. Sorry, uniform convergence. Don't get confused, by the way. Uniform continuity is different from uniform convergence. But before doing it systematically, can you see by this picture that this is uniformly convergent? So, for example, let me just do this problem. So, problem 14.9. So I have given you a function, a sequence of functions, 0, 1 to R, and I have defined them for you in this form. Okay? So we want to show, by the way, they have told you that what function is that. By the way, here 0 is not the number, here 0 is the 0 function. So this is what we want to prove. Okay, so here we want to prove this. Rigorously I want to prove it, but we can draw this picture to see how it goes. So let us try to understand it from graphical point of view. This is always good to see if it is uniformly convergent or not. So my domain is from 0 to 1. So here is 0, for example. Here is 1. Okay, and what is the candidate? It is 0 function. 0 function is this one. The graph of the 0 function is this one. This is the function f of x equals to 0. Let me choose one epsilon and go epsilon upward, for example, and epsilon downward, okay? And then I want to shift this limit function epsilon upward. It becomes this function, and epsilon downward, yes? So this length is epsilon, this length is epsilon, okay? Something like that. Okay, let me fix one n and draw the graph of one of them. For example, n is a fixed number. This is a line that passes through the origin. So this is the origin. Let us say that I put 1, so f becomes 1 over n. Let us imagine that 1 over n is here, okay? So this is my line. Yes? If I ask you what is this one, this is the graph of f of n of x, which is x. Yes? So you see, this one already is sticking out from this band. But let me try to increase n. So what will happen when I increase n? When I increase n, this line becomes this is fixed. It's like a hinge, and it will start rotating and coming down. Okay? So at some point, I hope that you agreed, if I increase this a lot, this line will somehow completely will be in the band. And if it becomes in the band, everything afterward will also be in the band. So, is that right? So this kind of idea is already telling me that this convergence is uniform. Okay, so it means that if I choose an epsilon, might be some of them are sticking out from the band, but if one of them lie completely in the band for some particular value of n, then for any larger n, all the graphs will lie in the band. So it's already an indication that this uniform is convergence. But if you want to prove it rigorously, how do you prove it? So we want to do more or less the same thing. So we say that let, so here, uniform convergence, where was the definition? Epsilon should come first. So I would say let epsilon be given. We want to prove that there is an n for every x. If n is greater than 1, that works. So let me start with be given. And I start with my error. And so f of n of x is this one. This is less than epsilon. So let me write it like this, is equal to fn of x is x over n. But here I am lucky, f of x is proposed to me. If it is not proposed, how can I find this one? I go to the pointwise convergence, find the candidate, and that is your candidate, okay? So then it becomes -0, and the answer becomes, because I am working with, so I am working in this one, so I don't need absolute value, so it becomes x over n. And my goal is to make this less than epsilon, but for every x. Okay, so be careful. So if I write it like this, and I would say that, okay, n should be greater than epsilon, x over epsilon, and I would say that, okay, n is a natural number greater than this one. Is that acceptable? No, because if you define it in that way, your n depends on x as well. You don't want that, okay? So you have to get rid of this x in your estimation. But that's extremely easy in this case. Do you agree that this one is less than or equal to this? Because I am working in this domain. So x is a number there. So this is definitely clear that x over n is less than or equal to this one. But my goal is to make this less than epsilon. Okay, if I make this less than epsilon, I am done. Because this is already less than that one. So I would say that let n be a natural number such that 1 over n is less than epsilon. Then, if n is greater than or equal than that n, 1 over n is also less than epsilon. And I am done. So this n, I didn't even tell you what that n is. I'm just telling you that there is such an n, and I am. Is that clear? Okay, good. So let us go to this one. So for example, from this picture perspective, I hope that you can see that this is not uniformly convergent. Yes? Can you see why? Can you see? It is that example. In this example, it was pointwise continuous, convergent, but now you will see it is not uniformly convergent. Why? Because this is your function. This is your function. So your function is 0 up to here, but it is 1 at one point. So this is your function. So now if I shift this by an epsilon, this function will go here, and this one will be shifted upward, yes, the same amount. And then if I go downward, this point will come down. Okay, so this is that epsilon band here. Yes, this is your band. But now, what type of functions I have? I have x to power n functions. So if I draw the first one, which one is the first one? The first one is just f of x equals to x if I put n equals to 1. Yes? Okay? So it is already sticking out from my band. But you shouldn't give up hope, yes, because you increase n. But when you increase it to x2, it becomes here. Okay? The chance of sticking out becomes smaller. But what is important is that no matter how I increase n, what happens, because of that one single point, there will be still protruding. I mean, there will be sticking out no matter how much I increase n. Yes? So if I increase n, this becomes steeper. And then you see that it is not possible to have all these graphs within this band. Okay, so it is intuitively clear that this convergence is not uniform. So it was pointwise, but it is not uniform. Okay, but how can we prove it rigorously? Again, we want to say that this is not the case epsilon delta proof, so we go with proof by contradiction, and let us say that if f n converges to f uniformly, then there exists an n such that for every x in 0 and 1, if n goes greater than or equal to n, then the difference between fn x minus fx is less than 1/2. So I am choosing something for epsilon, okay? So that I can have the contradiction. Can you see that why that's a contradiction? Which number you choose, you want to, so it means that if you agree that this is the case, you have to agree for every epsilon, including 1/2, this should work. And then you have to seek for something that gives you a contradiction. How do you seek for that?
We find an x where this doesn't
But
work.
in the exam, you have to give me that x.
Yeah.
So what x is that?
X equals to 1.
No, x equals to 1, it is not contradiction because f of 1 is unfortunately 1.
Oh.
Yes? Is it?
Yes.
F of, is that 1 working? So what is fn of? It's because 1 minus 1 becomes 0. 0 less than 1/2 is not a contradiction, unfortunately. Okay? But you are right, we have to give it x. What x we provide?
X arbitrarily close to 1. So like
Yes.
0.9 should be, I don't know, like close enough to 1.
No, but this you have to express it in terms of this n, because n is not, you don't know what n is. So you don't know where it is actually protruding out, yes? Because you don't know how big n is. You know there is an n. So the x that you provide for me, you should depend on x. It should depend on n. Yes, because this x should depend on n. Okay, so what does it mean? For example, let me see if I can do it or not. Let us choose x to be this number. Okay? And then if I put it there, what happens? No, I want to, so, because then this one becomes 0, that is good, that's not a problem. And I want to make it a number so that x to power n becomes less than 1/2. Yes? So if I am looking for x, so x, okay, I will take it like this. Yes? Is that right? Let us check. Okay, so what I'm saying is that if you don't believe that this cannot be uniformly convergent, then you have to believe that there is one fixed n at least that this works for that particular epsilon. Then what I am saying is that let x be equal to 1 over the nth root of 2. Okay, what is this n? The n that you have to admit it exists if you believe the convergence is uniform. I take that n and I construct a number. Okay, this number is here. Do you agree? Okay, this is in 0 and 1. Okay, then it means that fn of that x minus f of that x absolute value should be less than 1/2. Yes? But what is this number? This number is just 1 over 2. Yes? And this number is 0. And that is the contradiction that you will look at. Yes? Is the idea clear? If you think about it, hopefully it will make sense. Okay, so this was my scratch paper work. Okay? Okay, so let us see what we have now. Okay, so this is one of the most important theorems. Let us do this one, then we will have a break, okay? This is a little bit more technical. I want to prove this one completely for you. If we have enough space, yes. So, uniform limit of continuous functions is continuous. So that is exactly the reason actually we become interested in the uniform convergence in the first place. Yes? what does it mean? It means that if you have a sequence of continuous functions that uniformly converges to a function, the limit function remains continuous. Okay? It is not bad like pointwise convergence. Here, this sequence of functions converges pointwise to this function, but not uniformly. And then you see that even though I start with continuous functions, the result, the limit function is not continuous. But uniform continuity, uniform convergence will not allow that. So that is the theorem we want to prove. The proof is technical. I want you to see it once. I hope that I can generate it on top of my head now. But let us see. So what do we have? We have Fn are the functions from D to R. And we know that f is also a function from D to R. If you ask me what D is just a subset of this one. And what I know that Fn's are, so let me write them on top of them. So it is continuous, all of them are continuous. And we know one more thing. We know that this sequence converges to F uniformly. We want to prove that F is continuous. Of course, on D. Yes, this is what we want to prove. When I say continuous, it means continuous on D. It means for every point. Is that clear? So that's what we have. Okay, so let us do the proof here. F is continuous on D. We want to prove that. How should I prove that F is continuous on D? I have to prove that F is continuous at every single point of D. So I would say let P belongs to D. We prove that F is continuous at P. Okay? To prove it is continuous at P, I have to start with epsilon delta definition. So I would say let epsilon greater than 0 be given. We prove what? We prove that there exists a delta positive, so that for every x in D, if absolute value of x minus p is less than delta, this implies that the absolute value of f of x minus f of p is less than epsilon. Yes? This is what I want to prove. I want to prove that f is continuous on D. It means that I have to check the continuity point by point. So I pick one point from D, and I want to prove that f is continuous at D. To prove this, I have to use epsilon delta definition of continuity. So I would say that let us choose one epsilon given. My goal is to convince you that you can always find the delta, so that this implication works for every x in D. If I can succeed that, it means that I have proven that this is continuous. Okay, now you have this mentality again like a factory that generates the numbers you want. Okay, so I start from here. So we have Fn converges uniformly to F, yes, on D. This is guaranteed. From here, by definition, what can I do? Do you remember what I have given you? I have given you an epsilon, and I am sleeping, and you are working on finding your delta. So I want to come back and ask for your delta. Okay? But you do what? You give this epsilon to this factory. But this factory generates what for you? It's on the board, yes? Where was it? Here. Epsilon, I gave it to you. It will give you an n, not a delta. Okay? But anyway, it gives you an n such that for every, where is it? Okay, here. For every x in D, if n is greater than or equal to n, then absolute value of f nx minus fx is less than epsilon over 3. So I gave you an epsilon, you divide it by 3, and give it to this, and it gives you an n. Okay? You have to be patient to see why. By the way, I told you before, you can write epsilon, and then you see that at the end you will have 3 epsilon. To get rid of that 3, you go back and rewrite everything in terms of epsilon over 3, and your final result that you want is epsilon. Okay? That's the trick. Okay, but now I want to get 2 immediate consequences of this. First of all, do you agree that what I am writing here is true? Based on that, if I write this one for you, do you agree for me or not? Do you agree with me or not? So number 1, I would say that for all x in D, absolute value of f capital N of x minus f of x is less than epsilon over 3. Do you agree with this one? Is it a consequence of this result? Because it tells you that if little n is n itself or greater, this works. So this means this works for capital N as well, for every x in T. This is one immediate consequence. Another consequence is, I would write it and I will ask your opinion about it. If I write this one, do you buy it or not? NP do you agree with this one as well? Yes, because this implication is true for n's greater than or equal to n, including n, and for every x in D. But P is one of the elements of D. So if it works for every element in D, it also works for P. Is that right? So these are 2 consequences I got. Okay, so I have used this piece of information and I got 2 results. So there's one piece of information I haven't used yet. Okay, and that is the continuity of Fn's. Okay, so now what I can talk about is this. Do you agree that F capital N is also continuous? Because it is continuous for every n, including that n you got from this. Okay, so we know that Fn is from D to R is for every n. This is continuous. So this means that F capital N is also continuous. Do you agree? And if it is continuous, it means it is also continuous at, no, we just stop here. It is continuous. No, let us continue. It is continuous at P. Okay. So now what we do, I want to write something. So therefore, there exists a delta greater than 0, such that what happens for every x in D, if absolute value of x minus p is less than delta, then absolute value of fn x minus fn p is less than epsilon over 3 again. Are you following or not? Yes, so I have written 2 consequences. These are important, but now I am saying that the n that I got it from here, I take it with me here because all of them are continuous. F sub capital N will also be continuous because it is just one of them. And if it is continuous, it is also continuous at P. Okay, then the existence of a delta with that property is guaranteed, because F sub n is actually continuous at P, and that's the definition of continuity in epsilon delta notation. Now, can you see what happens now? Do you remember what we were looking for? We were looking for this delta. Now, I'm claiming this is my delta. Yes? That is what we want to prove. So let us just prove this one, and then okay, we can stop here because I have to clean the board. Okay, so we can have a pause and then we come back. Thank you.